Dear colleagues, the subject of my talk today is all-fiber generation of optical vortices via acoustically-induced helical gratings. This work has been carried out in collaboration with Professor Konstantin Alexeyev and postgraduate Dmitry Vikulin at Institute of Physics and Technology of Crimean Federal University. Let me start with explaining the motivation of the work. The possibility of interaction between light and acoustic waves, the so-called acousto-optic interaction, can be used for light control. Indeed, frequency shifters, wavelength tunable filters, deflectors, and intensity modulators have been implemented both in the bulk and fiber configurations. The last case is special because the fiber guides both acoustic and optical waves. These provide unique conditions for a highly efficient and versatile acousto-optic interaction, thus ensuring the valuable advantages of the fiber scheme. At certain fiber parameters, the scalar approximation can be used, thus treating the standard LP states as unperturbed fiber modes. The commonly known scalar effect induced by a flexural acoustic wave in circular fibers is the complete transformation of the fundamental mode to the higher order one and vice versa. The generated field can be downshifted or upshifted in frequency. Quite recently, we proposed a new model of the fiber acousto-optic interaction, which opens up new possibilities in controlling the optical vortex beams. Indeed, let the fiber is tuned in to the acoustic resonance. If the optical vortex, polarized orthogonally to the acoustic vibration of the fundamental flexural mode, be excited at the input end of the fiber, then at a given distance it comes unchanged. Changing the polarization direction ensures topological charge flipping. So, the incident polarization governs the topological charge and orbital angular momentum of the generated beam. In the true vector case, the phase velocities of unperturbed fiber modes are strongly spaced, so that there are a few different acoustic resonances. In the so-called vortex resonance, a right-handed circularly polarized fundamental mode is totally converted into the frequency downshifted optical vortex of the topological charge +1 on the same polarization. Changing the sign of input polarization gives rise to the appearance of the left-handed circularly polarized optical vortex of the topological charge -1. So, one can unveil the spin-dependent mode conversion where both polarization and topological charge of the generated vortex beam are determined by the incident polarization. The experimental evidence of this mode conversion was recently reported. The main possible application is the all-fiber fast dynamic control of simultaneously both spin and orbital angular momentum of the vortex beam. The modern orbital angular momentum based information technologies require operating with optical vortices of the higher than unity topological charge. This issue can be addressed by invoking the higher order acoustic modes. We begin with considering the standard circular fiber model with the following permittivity. The equation of motion for a homogeneous isotropic circular rod has a solution in the form of linearly polarized acoustic vortices with topological charge ±1. Here U0 is the amplitude-like factor, omega and k are the frequency and wave vector of the acoustic wave correspondingly. The deformation wave modifies the unperturbed fiber permittivity in two principal ways. The first modification is connected with a pure geometrical displacement of physical points of the unperturbed fiber, which can be allowed for by making use of the following coordinate transformation. The second acoustically induced effect is the change in the optical properties of a fiber material due to stress via the photoelastic effect. Combining these two effects, we arrive at the complete expression of the desired permittivity. Please note that the tensor-like correction happens to be independent on the polar angle and hence cannot provide a coupling of different optical modes. Further, we aim at obtaining the fiber eigenstates. Using the ansatz, one can get rid of the time and z dependence in the scalar wave equation, which then can be brought to the form of the eigenvalue equation. Here the first operator gives the scalar approximation to the unperturbed fiber modes, and the second one accounts for the acousto-optic interaction. The following relations allowed us to use the so-called resonance perturbation theory to solve the given equation. The zero-order equation yields the vortex modes of the unperturbed fiber with all the possible frequency and azimuthal numbers. At that, the propagation constants prove to be modified so that they become dependent on the acoustic k-vector. The key point of the resonance perturbation approach is that among all the zero-order modes, only those with almost the same propagation constants can be coupled efficiently by the perturbation. Such a spectral property is also known as the accidental degeneracy. Yet, the acoustically induced matrix element should be non-zero. From these two conditions, the resonance values of the acoustic k-vector, as well as the selection rule for the coupled modes, can be obtained. A few mode fiber will be further assumed. In the acoustically free fiber, the mode levels have the structure depicted by two black lines. When the acoustic wave is on, the level of frequency downshifted, higher order modes goes up, intersect the fundamental mode level, and interact with it, thus forming the first resonance point. The corresponding two first modes are found to have the following hybrid structure, where sigma specifies the direction of circular polarization. Analogously, the frequency upshifted fundamental mode level goes down and gets intersected with the higher order state, thereby creating the second resonance point with the two last modes. Note that the parameter theta comes from the interplay between the detuning and the coupling strength. Naturally, the strongest coupling occurs at the resonance condition. Now, let the acoustic topological charge be set to +1. The obtained solutions predict that the incident fundamental mode at a given distance gets transformed into the frequency downshifted optical vortex beam of topological charge -2 with 100% efficiency. If then the acoustic topological charge is switched to -1, the incident zero-order beam will be completely converted into the frequency downshifted +1 charged optical vortex. Generally, we unveil a novel, all-fiber, efficient optical vortex producing directly from the Gaussian-like mode, in which the outcoming topological charge and orbital angular momentum is governed by the topological charge of the acoustic vortex. These findings can open a path to implement new acousto-optic devices for dynamic controlling the vortex beam parameters, what should be especially useful in such applications as micromechanics, classical and quantum information encryption, and simulation of quantum computing. It should be pointed out that this conversion has a somewhat enigmatic feature, as the created topological charge occurs the double of that of the acoustic vortex. To explain this fact, one has to note that the described optical vortex generation can be viewed as a result of the diffraction of the incident beam on the acoustically induced long-period fiber grating. Further, the permittivity correction is presented in a more physically meaningful form, where the first term describes the well-known helical gratings of the twofold rotational symmetry. Such gratings have been shown to have the ability to change the incoming topological charge by 2 units. On the contrary, the second term appears to be phi-independent, thereby being not capable to change the mode's order. To complete, the left figure shows that the vortex production reach the maximal efficiency at the resonance and for fibers of some optimal length. From the second plot, it's seen that in the opposite situation, the local maxima can still be reached at some non-zero values of detuning. Finally, the right drawing is to demonstrate that the generation process is wavelength tunable and can be used for vortex intensity modulation for changing the acoustic power. So here is the summary and finding information. This work was financially supported by the Russian Ministry of Education and Science Mega Grant Project and by President of Russian Federation's grant, and at last by Crimean Federal University grant. Thank you for your attention.